We studied the multipole expansion of the electromagnetic wave in the free fields without any source. Today we are going to include the sources. So if we summarize what we have done, we start with the wave equation. We converted this wave equations. You can go over your lecture notes to the scalar wave equation, taking the scalar product with the left hand side using the some calculus. We find this solution of the scalar wave equations, and we come to the following point. So we did the same thing for the electric field also. So if you go over your lecture notes, the points for the solutions of the fields for the source-free region. Source-free means that there is no any source on the right-hand side. So the H field could be written in terms of multipole expansion, some coefficients which depends on the Lm, spherical Basel functions, x Lm, where x Lm was 1 over square root L times L plus 1 L y Lm. L is the angular momentum operator, but we are just using the eigenvalues. So this is a tool so we use the L in order to understand in order to use the eigenvalues, because we know that the L square y Lm is equal to L times L plus 1 y Lm. And what else we find? Z0 impedance of the free space, Am, Lm, curl of, so Z0, there is no Z0 here actually. Spherical Basel function x Lm. So we did some work and we derived this. So AE and AM are corresponding to transverse multiple orders of electric field and magnetic fields. So what we are going to do, and last time I have shown you that how you can find these coefficients using the orthogonality. That was simple. Take the scalar product with x Lm, L prime, M prime, and integrate through all solid angles and use the orthogonality conditions and solve these coefficients. So basically the solution of AE or AM could be explained in terms of H dot R and E dot R. So today, first, I will investigate the form of the radiation power emitted per solid angle at the far field zone. So basically, if you go to the far field zone, Kr is much greater than 1. So this stuff is done in last time, so you can go over your lecture notes. So in the far field zone, GL Kr and FL Kr has the asymptotic forms. They are minus I L plus 1 e to the I Kr over KR. And you can plug this information to the definition of the H, and also instead of curl operator you can write I, K, and cross. So basically I and I is minus, K and K cancel, and if you plug this information there, your H field at the far field zone will take the following form: e to the IKR divided by KR, summation through the L and M, L 0 to infinity, M minus L to plus L, and take the things to the parentheses of minus I to the L plus 1, and you will have AE LM X LM plus AM LM and cross XLM. So this will be the form of the H, and as you see that it has the spherical wave term. And you know that what should be the electric field in the far field zone? E and H and Z, E electric field, magnetic field, and the propagation direction are mutually orthogonal to each other. It is Z0 H cross N. And if you calculate that the power emitted per Salt angle, so that is 1 over 2 real part R square N dot E cross H complex conjugate. So if you take this and put it there, but before going to do put inside plug-in, so if you substitute this information here, you will have H cross H, and that is equal to using the double cross product rule, that you are going to obtain Z0 over 2 R square H square. Now if you plug this information to here, so if you take the absolute value of this, e to the IKR will be 1, and this should be 1 over R square, cancel with that R square, and you will have 1 over 2 K square times Z0, power emitted per Salt angle will be Z0 over 2 K square, R square terms will be cancelled, summation through the L and M, e to the minus I L plus 1 AE XLM AM and cross XLM, you will obtain this. So basically, first thing today, we will look at the power emitted per Salt angle, and the next we will try to solve the coefficients if this wave equation is non-homogeneous, if there is a sources. So if you look at here, if you think that you have one mode, AE or AM, the property of the AE, one of them has the transverse electric field, the other only transverse magnetic field. And if you think one of them, AE or AM, you can write this in the following form. So this is equivalent to Z0 over 2K square summation through the L and M, or say that wait a second, say that, let's say that this is, let us say that this is as for any coefficients, not this whole summation. So take this to the inside. So power per solid angle for each Lm values. So you can think about that this is the power per solid angle for each Lm value. So if you want to write this for just multiple order Lm, that could be written as Z0 over 2k square AE or AM Lm x magnitude x Lm square or x Lm cross n cross x Lm square. So what I did here, so basically you can take this to the inside and you can call the all inside is power emitted per solid angle for each Lm values. Okay, so you take this to the inside summation and say that the absolute square of the summation of the power emitted per solid angle each multiple order Lm, and your expression in that form. You have either the choice of A sub E or A sub M. One has the property of the transverse electric field, the other has the property of the transverse magnetic field. If you choose this A sub E, that should be x Lm square. If you choose that the AM, that should be what? N cross x Lm. But you know that the x is parallel to the L and N is perpendicular to the L. I show you that N dot L is equal to 0. Okay, so basically this is 90 degrees. So basically this absolute square is equivalent to the absolute square of the XLM. Now I will estimate the power emitted per solid angle each multipole order Lm. So I need to calculate XLM square, XLM square, and I know that the XLM is 1 over square root of L plus 1, L acting on YLM. So basically this is equivalent to what? X component of Lm square, Y component of the Lm square, X Z component of the Lm square. And if you write this in terms of this L acting on the YLM, that is equal to 1 over L plus 1 Lx YLM square Ly YLM square Lz YLM square, close the parenthesis. And you know one other thing, Lx. You know one another thing, L plus or L minus is equal to Lx plus minus ELY. Okay? So basically, Lx is nothing but L plus L minus over 2. Ly is L plus minus L minus over 2I. So you can solve that the Lx and Ly. So you did this in quantum mechanics. And you know that the eigenvalues of the L plus and L minus and Lz. So if you apply this, you are going to obtain the following. So what I am trying to do, I said that total power emitted per solid angle is equal to summation of the all multiple orders, including the coefficients. But then I said that let inside this term be power emitted per solid angle for each multiple order Lm. And I find that this is proportional to x square, xlm square. Now I will calculate that the xlm square quickly, and I will discuss about the distribution of the radiation each multiple order. So if you open these terms, you will get the following: 1 over L plus 1, and this will be what? 1 over 4 L plus YLM square, and the other term will be 1 over 4 L minus YLM square. The cross term will be plus 2L plus L minus over 2 YLM. So I open this square. If you do the same thing to the second one, you will obtain 1 over 4 L plus YLM square, 1 over 4 L minus YLM square. The cross terms will be what? So the cross term will be what? So this should be only minus, because if you solve from Ly here, you will obtain that. So if you take the cross, the square of this term, this cross product of these two cross term will be minus L plus L minus YLM, and the last term will be plus LZ YLM square, close the parenthesis. So basically these two terms will be cancelled, and these will be the 1 over 2 and 1 over 2. So the bottom line will be the following. So L plus operator acting YLM, L plus operator acting YLM is equal to square root L minus M, L plus M plus 1, YLM M plus 1. And the other one, L minus operator acting YLM, is square root of L plus M, L minus M plus 1, YLM M minus 1. We have 2 times of this, and you know that this is M YLM. So basically, if you want to look at the power emitted per solid angle for each multipole order, should be the following. You have the coefficients as 0 over 2k square from here. You don't know the A. I will show you that how we can calculate it. So you have 2 possibilities. That could be AE, LM, or AM. And the rest will be this 1 over 2 of the square of this term. You have to take the square of this, and you have to take the square of the other term. So basically, you will get the following. Open a parenthesis, 1 over 2, because you have 1 over 4 here, 1 over 4 here. If you add up, that will be 1 over 2, and taking the square of that will have the following formula: L minus M, L plus M plus 1, Y LM LM plus 1 square. This is the first term, square of the first term. The square of the second term will be 1 over 2 L plus M, L minus M plus 1, Y LM M minus 1 square. And the last term will be M square Y LM square. And close the parenthesis. So this is the form of the angular distribution of the radiation at the far field zone in terms of multiple orders. What we did, we said that electric field H and the propagation will be mutually orthogonal to each other. Power emitted per solid angle should be related to the full field of the H square or related with the electric field square. And if you plug the H here at the far field zone, you have the two possibilities: transverse electric and transverse magnetic. So in both cases, they are related to some unknown coefficient and times the square of the XLM magnitude. And XLM could be written in terms of the L operator acting on YLM. We know that the eigenvalues operator when that is L plus or L minus or LZ. So the eigenvalues are this. So this rises to M1, this lowers to M minus 1, but the LZ doesn't touch the M, leave it is there. Is it there? So this format will be the power emitted per solid angle each multiple order. So basically, at this point, I will show some specific examples. So if you look at the power per solid angle for specific case, L equal to 1 and M could be 0 or M could be plus or minus sign. M equal to 0, you will get this if you put M equal to 0, L equal to 1 there, and if you look at the angular distribution of this, you will obtain 3 over 8 pi sine square theta. How many poles do you have as a function of theta? So if you look at it as a function of theta, you have 2 poles. So that is sine square theta, and the functional form is the following. So if you say this is the z, theta is measured from the z-axis. So when the angle is 0, sine theta is 0. So sine theta is maximum when the angle is pi over 2. And if you go to the other branch, you will have the symmetric of this. So basically, L equal to 1, M equal to 0 is identically corresponding to the dipole radiation. So, and for this particular case, the dipole is oriented along what? Z-axis. And if you look at the distribution L equal to 1, M plus or minus 1, the situation is more complicated. 3 over 16 pi, 1 plus cosine square theta. And again, you have 2 poles here. And in that case, the poles are more complicated. L equal to 1, M equal to plus minus 1 has this structure. What is the structure? So more complicated structure. So that is something like this. But basically, this is m plus 1 and m plus 1 or m minus 1 is corresponding to the following. If you have z-axis, x-axis, and y-axis, L equal to 1, m equal to 0 is corresponding to your dipole along the z-axis. L equal to 1, m equal to plus 1 is the dipole along the x-axis, and minus 1 is representing the electric dipole along the y-axis. And if you look at the angular distribution, if you put your dipole along the x or y, and if you look at the distribution along the z-axis, you will have some different structure, something like this. So actually, this should be symmetric. Up and down should be symmetric. So I am sorry, I am not good in drawing. Okay, you can look at your book. So basically, all stuff related to L equal to 1 is the dipole radiation. So if you make a measurement, if you get the pattern exactly, you can have a feeling about what kind of the radiation you have, what kind of the source you have. So even you have a dipole radiation, you have different angular distribution. So if the dipole is along the z, this is a perfect sine square. If the dipole is along x or y, you have more complicated structure. L equal to 2 in here, and m equal to 0, m equal to plus 1, and you have another option, m equal to plus minus 2. Okay, you are the possible options. And all of them different structures. So for example, this one is L equal to 2, m equal to 0 is 15 over 8 pi sine square theta cosine square theta. So what is this sine square theta and cosine square theta? Do you remember? So when we studied that the electric quadrupole radiation, we obtain a coefficient sine square theta and cosine square theta. That means that you have 4 poles for that case. So if you say this is the z-axis, so you have one pole here, the one pole here, and another here, and another here. This is corresponding to that. And L equal to 2 is corresponding to quadrupole radiation. Quadrupole radiation. And if you look at those things, these are more complicated, but all L equal to 2 stuff is related with the quadrupole radiations. If you go to the L equal to 3, probably there should be what? One higher of the L quadrupole should be what? Octuple, I think. So nice thing, you can get the correct radiation pattern and you can get the correct source distribution, but I haven't come at that point. But what we plot here, we plotted that the power emitted per solid angle each multiple order L. We haven't touched anything to the coefficient. We don't know the coefficient. We said that if L equal to 1, m equal to 0, with this radiation we have. If L equal to 1, m equal to 1, we have quadrupole radiation and so on. But basically, we should be able to find these coefficients. We can understand that which contribution is significant if we know these coefficients. And this is a full expansion in terms of unknown coefficients. So this is the structure of the radiation where in free medium. But now we have to put the sources. So we will put the sources, we will rewrite the wave equation, and we will look at the solution, how would be the solution, and we will stop there. So we know that how to do multipole expansion. We know that the fields in free space in terms of the multiple expansions, and we have a feeling about that the radiation patterns of the multiple expansion. Now let us add up the source. and see what is going on if we add the sources. So, sources of multipole radiations. Basically, sources could be charge density, oscillating frequency omega, current density, and that could be also magnetization density. So these are the possible sources. So let us write the Maxwell's equations again. So we know the magnetic monopoles, there is no magnetic monopoles. So I will write the form of the Maxwell's equation which I want on the left. So let me say del dot H prime. I will put a prime. We will see that why we needed the prime in a moment. Just wait. So this is the first one. The second set, divergence of electric displacement is the charge density. And let me write here. Here I have sources, because then I cannot write del dot D is equal to 0. So in free medium, we were writing that the charge density is 0, but now we cannot do. So let me write this as a divergence of E, not E prime. I will show why I am doing this, as a rho over epsilon 0. This is the second set of Maxwell's equations. This is a scalar equation, this is a scalar equation. And the other one, Faraday's law, curl of E plus del B over del T is equal to 0. How many equations we have here? This is a vectorial equations. We have 3 independent equations. So actually the Maxwell's equations could be said as 8 equations, 8 independent equations. 3 for Faraday's, 3 for amperes, modified amperes, 1 for this, 1 for the other one. 8 independent equations, you can tell. So let us put this the form which I wanted. So this is, if you put the oscillatory term, if you say that the field is oscillating as e to the minus I omega t, that is nothing but minus I omega b. And so omega is, what is omega? Omega is Kc. Omega is Kc. Yes. And C is 1 over square root of mu 0 epsilon 0 multiply by mu 0 divided by mu 0 this. So this becomes H, and one of the mu 0 goes up because mu 0 over square root of mu 0 makes the square root of mu 0 over epsilon 0. Basically, this should be minus IK impedance of the free divided by the impedance of the free space. So the Faraday's equation, this third equation, will be curl of E minus IK Z0 H prime is equal to 0. So this term is the H. I call as a H prime. Mu 0 over square root of mu 0 is the square root of mu 0 divided by square root of epsilon 0, that is the impedance of the free space, and we have the minus sign coming from the del over del T. And the fourth one from the modified Ampere's law will be the following. I have curl of H is equal to current density of the free current density, free currents, plus magnetization current density. This is the magnetization current density, which you know from the first part of the course. And you have del D over del T, change of the electric displacement in time. So basically, again, if you do the same thing we did, this will be minus I omega. Omega is Kc. C is square root of mu 0 epsilon 0. D is epsilon 0 E. And in that case, one of the epsilon zeros will be cancelled. That will be square root of epsilon 0 over mu 0. If you take the term to the other side, you will obtain curl of H prime. I am saying that the H is H prime in a moment. Take the stuff to the left, that will be plus IK E now divided by the impedance of the free space, and the leftover terms is the current density, free current density plus magnetization current density. Now I will start to play these equations and to form the wave equations. Now I can erase the old stuff here and let us start to study to derive the wave equation again. The problem here, del dot E is not equal to 0. So what I am trying to do, I will write a new field E, which is shifted. So E prime is shifted by some imaginary number J. If I shift the E field that amount, I will get a very nice things, because what is the nice things? What I needed here, del dot E prime. So del dot E prime will be del dot E plus I omega over epsilon 0 del dot J. What is del dot E? Del dot E is rho over epsilon 0 here. And what is del dot J? From the continuity equations. What is this? From the continuity equations, del rho over del T, that is minus I omega rho. That is I omega rho. So del dot G is equal to minus del rho over del T, del over T minus I omega, minus, yes, that is plus. That makes plus, and I is minus, omegas are cancelled, and that is 0. So if I define a new field as a E prime, I can make this Maxwell's equations without any divergence, okay, and that helps for me to derive the wave equations. I shift amount and I use the continuity equations. So say that now divergence of E prime is equal to 0 under this shifting the field. Then the rest is easy. We can derive the wave equations much more easy. So I use the property of the continuity equations and shift the field by an imaginary number and make the Maxwell's equations without any source. Source is there, but it seems to be a source. There is no source there. So now let us work with this third equation. So pick up the third equation. So instead of E, write as curl of, instead of E, write in terms of the E prime, that will be curl of E prime I omega over epsilon 0 current density is equal to or minus I k Z0 H prime. So basically this is nothing but the following. That is equal to curl of E prime minus I k Z0 H prime is equal to what? I over omega epsilon 0 curl of J. So I write all Maxwell's equations with the primes. Now let us pick up the fourth. So I will try to combine these two equations to write the wave equation. So let us pick up the fourth equation. So fourth equation is there, and take the J to the other side. So that will be what? Curl of H prime. Take the J current density to the left. Take the IK over Z0 parenthesis plus IK over Z0 parenthesis. That will be what? E minus Z0 over IK current density. I take this to the left and take the IK over Z0 parenthesis. That should be equal to, whole stuff should be equal to curl of magnetization. So if you take this to the left. So you can see one thing here nicely and quickly. So this term is equivalent to, take the I is up, that will be plus. Z0 is mu 0 over epsilon 0, and omega over k, it's C, omega kc or omega over kc. So this is nothing but impedance of the free space, and then 1 over k is nothing but C over omega, and go one more. So this is I mu 0 over epsilon 0 in the square root of 2, 1 over omega, 1 over mu 0 epsilon 0. This term will be cancelled, and these two terms will be epsilon 0, and altogether if you take the E plus I over omega and this epsilon 0 and multiplied by current density. Okay, so go step by step. Z0 is square root of mu 0 epsilon 0. K is 1 over k is C over omega. C is 1 over square root of mu 0. Mu 0 is cancelled and you obtain this. And this term is nothing but the displaced electric field. So basically, now we have the sets of Maxwell's equations in terms of shifted frames, frames. So that would be nothing but curl of H prime Ik over Z0 E prime curl of magnetization. So now we are ready to derive the wave equations. So how we are going to do? The standard, take the curl of the one of them, plug the other one to the inside and combine the things. So if you take the curl of H prime, you have here Ik Z0 curl of E prime and curl of magnetization. So you know that the curl of H operation, that is gradient of divergence of H prime minus Laplacian of H prime. If you take that the curl of E prime, what you are going to obtain? Gradient of divergence of E prime, and again that will be 0. Okay. So here you have I k over Z0 curl of E prime. Above, pick up the curl of E prime. So that would be what? I over omega epsilon 0 curl of J. Take this to the right hand side, you will obtain I omega over epsilon 0 curl of J plus Ik Z0 H prime equal to curl of magnetization. So I plug the curl of E prime to here, IKZ0 here. That is nothing but I omega over epsilon 0 curl of J and plus IKZ0. So as you see that divergence of H prime is 0, no magnetic monopoles. Z0 and Z0 will be cancelled. I and I will be minus k square. So you will have the wave equation term here, minus Laplacian of H prime minus k square H prime. And this goes to the other side, and that will be the non-homogeneous wave equations. But before going to go one more step. For that term, you have Z0. Basically, this is cancelling. This is not cancelling. So Z0 is square root of mu 0 epsilon 0. I am concentrating on that term. K is omega over C. Omega over C means that the omega over C, so that should be upside down. So if it goes up, that is nothing but epsilon 0 mu 0. So 1 over Z0 is mu 0 epsilon 0, but take the up, so that will be what? So this is nothing but epsilon 0 mu 0, and therefore there should be epsilon 0 over mu 0. So this is the inverse of the Z0. This will be the epsilon 0 over mu 0 if you take this up. So basically mu zeros will be cancelled, that will be epsilon 0, and that will cancel with term, and omega will be cancelled that term. So if you consider this multiplication, so omega epsilon 0 will be cancelled. If you consider the other multiplication, that will be minus k squared z0. So then that means that you have a non-homogeneous wave equation. So that is minus Laplacian of h prime, and here minus k square h prime. So multiply with minus, make the positive. So that should be Laplacian plus k square h is equal to what? If you take this to the other side, and multiply with minus, you will get minus curl of J plus curl of magnetization. So I and I is minus, goes to the other side positive, and if you multiply everything with minus, that will becomes minus again. So if you compare what we have done previously, we obtain a non-homogeneous wave equation. We know how to solve because we know that the Green's function. Then we know how to find that the coefficients. So if you do the same algebra for the other, what we are going to do, you will take the curl of this, curl of E prime, and you will open this gradient of divergence of E prime minus Laplacian of E prime. Divergence of E prime will be 0. Do the same algebra and find that the other wave equation. That will be minus I z0 k curl of magnetization plus 1 over k square curl of current density. So we have now non-homogeneous wave equation. So I am not fully solve this. I will write the formal solution, and I will show you how we are finding that the unknown coefficients for the full solutions after the break. If I have a time, then I will start a new chapter, which is scattering.